Swayam Prabha. Digital India. Educated India.
Welcome back, students. So in the last class we were discussing design of continuous bioreactors. So we'll continue the same topic. Let's begin with the model for plug flow reactor, which is the kinetics is like a batch reactor, but the flow is continuous, which means that the substrate is continuously being fed in, and as it moves through the tubular reactor, the substrate gets converted to product. So the ideal plug flow reactor model equation is the same as that of the batch reactor equation. Real time in batch reactor design equation is changed to the residence time in the plug flow reactor. Ideal plug flow reactor cannot be operated with sterile feed. So if you see the slide, the picture on the slide, the length of the tubular reactor is L. The inlet substrate which is being fed inside the tubular reactor is S0, and because it is not sterile, the biomass concentration is X0, and as it comes out from the other end, the substrate gets converted and the residual substrate concentration therefore changes. So the outgoing substrate concentration has been represented as S, and the biomass due to growth, due to substrate consumption, has changed to X from X0. So it is an ideal plug flow reactor. If L is the length of the tubular reactor and V is the linear velocity, then the residence time be calculated as L by V of this plug flow reactor. The batch reactor design, we have already established the design equation as shown on the slide, given as equation 1, where A and B were constants which involved rate parameters. For a continuous reactor, we know now the residence time of this plug flow reactor can be given as L by V, where L is the length of the reactor and V is the linear velocity. Now this batch equation can now be written as, so we can substitute this T in the form of tau, which is the residence time given as L by V, and A and B were the constants based on kinetic parameters and your inlet biomass and substrate concentration. So let's see how and in what situations we need to use the plug flow reactor model. Now let's assume that it is a sterile feed in a combination of two reactors. The first one is the continuous reactor, ideal CSTR, followed by a plug flow reactor, an ideal plug flow reactor. So I said the incoming stream, we are assuming it is a sterile feed, and the inlet substrate concentration for the first reactor will be represented by the subscript 1, and for the second reactor the variables have been represented by subscript 2. So being sterile feed, Cx1 is 0, but there is Cs1 as the incoming substrate feed inside the continuous reactor with a volume V1. So because it is an ideal CSTR running at steady state, we have already now deduced that dilution rate becomes equal to the specific growth rate of the culture in a steady state CSTR. So if we again use a subscript 1 for the first reactor, then the dilution rate in the first reactor will become equal to mu1, where mu1 is the specific growth rate of the culture in the first reactor. Now, if the culture is following Monod's kinetics or Monod's model, we can further expand mu1 in the form of Monod's model, which is a function of substrate concentration. So, now the substrate concentration inside the reactor is CS1. Now, because it is an ideal steady state CSTR, whatever is the concentration inside the reactor will be the same concentration which is coming outside the reactor, which we are giving a notation 1. The inlet substrate feed has been given the notation CSI, and CXI, because it is a sterile feed, is 0. So, if you see this equation 1, it is in terms of the dilution rate, the specific growth rate of the culture in the first reactor, which is again an inverse of the residence time of the first reactor, which has been represented as tau 1, and it has been further expanded. The mu has been expanded as a function of substrate concentration inside the reactor at steady state as CS1, because it is following Monod's kinetics. Then CS1, therefore, after rearrangement of this equation, equation 1 can be represented under steady state as a function of residence time and culture kinetic constants. So, now if CS1 is known and the yield coefficient is known for the culture, we can find out the outlet biomass concentration from this first CSTR. So, as a function of the inlet substrate concentration and the outlet substrate concentration, and by X by S, we have determined CX1 because CXI here goes to 0. So, this is how we can determine now CX1. And similarly, if we know the yield coefficient by P by S, this we already know. Assuming the initial some product is already there, which has been represented as CPI, which can you also assume as 0, then your outgoing product concentration or the product concentration in the outlet stream can again in a similar manner can be represented as shown in equation 3 as a function of again the inlet substrate concentration and the outlet substrate concentration and yield coefficient of product with respect to substrate consumed. Now, we have already come to know what is the substrate concentration, product concentration and biomass concentration coming outside reactor 1, which is now an inlet to the reactor 2, which is a plug flow reactor. The volume has been represented as V2 of this plug flow reactor. The outlet substrate and the biomass concentrations in this ideal plug flow reactor have been represented as CS2 and CX2, and the inlet we know now are the outlet from the first reactors for this reactor, which is CX1 and CS1. Now, residence time for the second reactor, because it follows batch kinetics, can be estimated as shown here. So, your residence time can be calculated by using the limits of the initial biomass concentration, which is the inlet biomass concentration, which is CX1, and the final biomass concentration from this reactor, which comes out of this reactor, which has been represented as CX2. So, the limits are for the Cx have been given as Cx1 and Cx2 of the integral, and Rx is your rate of reaction. So, the biomass formation rate So, now if you will substitute this biomass formation rate is nothing but mu times Cx. It has been substituted here in place of Rx, and then integration has been done after substituting mu in terms of Cs. So, now this has two variables Cs and Cx. Now, in order to integrate this, we first need to remove one of the variables or substitute one variable in terms of the other. So, for that we again have another equation of yield coefficient Yx by S, which shows Cx2 minus Cx1 by Cs1 minus Cs2. So, the numerator is the amount of biomass produced in this batch reactor and the denominator is the amount of substrate consumed in this batch reactor. So, using equation 1 and 2, so 2 has been used to substitute Cs in terms of Cx, and then the equation 1 can be integrated and solved, which will lead to again batch design equation, which will take this form as given in equation 3. And A and B we have already seen in batch reactor design will be constants which are a function of the inlet substrate and biomass concentration and yield coefficients with Monod's model parameters. Now, tower 2 here was the residence time of the plug flow reactor. So, now once we have these two equations which can be used for the plug flow reactor and for the CSTR, if suppose tower 2 is known, which means the residence time of the second reactor is known, then the two equations can be simultaneously solved to get Cx2. The two equations, equation 2 and equation 3. Now, equation 3 has been obtained from equation 1. It is the same as the batch design equation. So, now there are two variables Cx2, Cx1, Cs1, Cs2 are the substrate variables. Now, Cs1 and Cx1 are known. There are two variables which are unknown Cs2 and Cx2, which we will use equation 2 to substitute one in place of the other and then solve the two equations, equation 2 and 3 simultaneously. Now, the second reactor is the plug flow reactor. For this plug flow reactor, the residence time can be obtained, can be given as, we know that Rx is dCx by dt for a batch reactor and Rx is the growth rate, which is mu Cx dCx by dt, which is the rate of accumulation of the biomass. Now, here residence time, once we integrate, let us assume tower 2 is the residence time, and here we have dCx by mu Cx. The integral limits, it is Cx1 and Cx2. Cx1 is the inlet biomass concentration and Cx2 is the outlet biomass concentration in this plug flow reactor. Now, further, because mu is following Monod's, can be represented by the Monod's model as a function of the substrate concentration. If we substitute here, so as shown here, we can write it like this. And once we now solve it, tower 2 is the residence time. This is nothing but your batch design equation, which we have already done earlier. And if you put your limits, then it becomes a function of CX2, CX1, CS1 and CS2. Now, in terms of yield coefficient, so yield coefficient of the culture was Yx by S, which is biomass produced per unit substrate consumed in this reactor. So, now we have two equations with two variables, unknown variables, which are CX2 and CS2. CS1 and CX1 are already now known from the first reactor. So, now we will substitute one variable as a function of other variable in any one of the equations. So, using equation 1, we will do the substitution in equation 2, and then if tower 2 is known, then we can simultaneously solve these. Now, let us see a case where multiple CSTRs are connected in series. A single CSTR can be divided into multiple CSTRs, assuming there are n such CSTRs linked together in series. Then for the nth steady state CSTR, the material balance for the biomass can be given as shown here. If F is the volumetric flow rate and Cxn minus 1 is the inlet biomass to the nth reactor, and Rxn is the reaction rate or the biomass formation rate in the nth reactor, Vn is the volume of the nth reactor, then at steady state the material balance of the biomass can be represented by equation 1, because there is no net accumulation rate happening. So, now Rxn can be expanded in the form of Monod's model. Another relationship between the X and the S can be obtained using the yield coefficient. So, for the nth stage reactor, we can have two equations. One is the mass balance for the biomass across this reactor, and the second is the in terms of the yield coefficient. The amount of biomass produced is in the numerator per unit substrate consumed in the is equal to Yx by S. The equations can be solved. So, now again similarly as we did earlier, the equations can be simultaneously solved with known cell concentrations and the dilution rates. The estimation of cell or substrate concentration with the known dilution rate can be done also by a graphical technique in this case. So, if you can see, the subscripts used for the nth reactor have been shown here. Cxi and Csi are the inlet to the first reactor, and Csn and Cxn will be the outlet from the nth reactor here. Now, for one CSTR, they have shown with this dark line the plot, if you see how the biomass formation rate will change. So, it will keep on increasing, it reaches its maximum and then comes down because of the substrate depletion. So, because this is a single CSTR, as the dilution rate increases, the biomass formation rate also increases, and then it reaches its maximum and very sharply goes to 0 at washout, shown as this point. Now, if this one CSTR can be divided into series of CSTRs, multiple CSTRs, then for the first reactor, if the dilution rate D1 is known, which is nothing but the slope of this line, So, if the slope is known, wherever this line will cut this curve, we can determine the biomass, the exit biomass concentration from that particular reactor. Again, if the dilution rate of the second reactor is known, then from this point another line can be drawn with that slope, and wherever it cuts the curve, again its corresponding x value will give us the exit cell mass concentration from that second reactor. So, if the dilution rate of each fermenter is known, then the cell concentration in each fermenter at steady state can be estimated by this graphical technique. Now, let us see, if we are running a continuous reactor with cell recycle, then how do we design such systems? So, the productivity in a CSTR is limited by the loss of cells from the outlet stream, isn't it? Because we cannot run a CSTR at dilution rates greater than mu max. So, the productivity is limited by the loss of cells which is happening in the outlet streams. Way therefore to increase the productivity can be to recycle the cells by separating the cells from the outlet stream. So, cell recycle therefore can improve productivity as the growth rate is a function of the dilution rate and the biomass. So, which is productivity. So, productivity is nothing but dx. So, if x can be continuously increased, then your productivity will increase, and it is proportional to the, because it is proportional to the cell concentration. So, cell recycle will improve productivity. Why? As the growth rate is proportional to the cell concentration. Rx is equals to d times x in a steady state CSTR. Now, mass transfer limitations can arise which may eventually limit the enhancement in productivity. As the cell concentration continues to increase, the steady state will never be able to reach. Okay. So, now we know that we can increase the cell concentration and therefore the productivity. But if you keep on continuously increase the cell concentration, the productivity after a while is compromised. Why? Because as the cell concentration will increase, mass transfer limitations will start appearing, and the mass transfer limitations can eventually then cause reduction in the growth rate of the cells and can limit therefore the productivity enhancement. Now, as the cell concentration is continuously increasing in such systems, the steady state is not able to reach. So, to operate such reactors in steady state, what we need is called a bleeding stream. So, let us design a continuous reactor with cell recycle. So, please note the schematic shown on the slide. The notations have been given as F0 for the inlet stream to the reactor, and Fr is the fraction of the stream which has been sent back as a recycle, and the cell separating device is at the outlet of the reactor as shown here as a small circle, oval shaped circle, and this is the stream which is going back as the recycle. So, please note the notations for the biomass, the volumetric flow rates of each of the streams, and x1 is the biomass concentration inside the reactor which is running at steady state. Therefore, the outlet is also x1 from this steady state continuous reactor. So, if you do a mass balance across the reactor, then you will end up in equation 1. Let's understand this. So, the first term is the rate at which the biomass is coming inside the reactor. The second one, now because it is a steady state CSTR and a chemostat, the flow rates have to be the same. So, here let's assume inside is Fr plus F0. So, your inlet stream here is being given as F0 and it is a sterile stream. So, that has been not considered. Then here the recycled stream has a volumetric flow rate of Fr with a biomass concentration of x0. So, the first term represents the rate at which the biomass is coming inside the reactor. So, they have not shown the term F0 into x, which is 0 because it is a sterile feed stream. Then mu x1 times V. So, V is the volume of the reactor, x1 is the steady state biomass concentration inside the reactor and mu is the specific growth rate of the culture. So, the second term represents the rate of increase of the biomass due to growth, minus F0 x1. So, x1 comes out of the reactor. So, it is the outlet. So, F0 plus Fr should be the flow rate outside the reactor if the volume is constant of this CSTR. So, this was F0 and this is Fr. So, it combines. So, the stream flow rate is F0 plus Fr. So, F0 plus Fr times x1 is your rate at which the biomass is going outside this reactor, loss, output, and it is a steady state, no accumulation. So, this is 0. So, input minus output plus growth in this is equal to 0 for this reactor mass balance for biomass. Now, again Fr by F0 has been represented as fraction A, x0 by x1, again this fraction has been represented as B, and F0 by V has been represented as the D, which is dilution rate. So, the F0, which was the inlet stream here, divided by the volume of this reactor has been represented as D. So, now if we divide this equation by the volume, there is Fr by V term into x0, mu x1, V gets cancelled, and again this has been divided by V. So, this is times x1. So, now all these have been brought in the form of F0 by V. So, F0 has been multiplied and divided in the first term. So, this has been then replaced as D. Fr by F0 given here has been replaced as A, and x0 by x1 given here. So, the entire equation has also been further divided by x1 and V. So, x1 has been divided. So, this fraction is then represented as B and x1 gets cancelled. So, this only mu remains in the second term, and on the RHS, F0 by V has been given as D And again in the second term Fr by V, F naught has been multiplied and divided, and again Fr by F naught has been, so F naught by V has been represented as D, and Fr by F naught has been represented as A. So now again D has been taken common. Inside we will have 1 plus A minus AB as the fractions, and on the one side only specific growth rate terms remains. So now if you see, for a continuous reactor with cell recycle at steady state, it is no more D is equals to mu, but it is a function of mu and the recycle stream flow rates and the inlet flow rate fraction Fr by F naught, where Fr was the volumetric flow rate of the recycle stream, and also a function of B, which is a fraction x naught by x1, where x naught was your biomass concentration in the recycle stream and x1 is your biomass concentration coming outside the reactor. So biomass separator, this device is a biomass separator. So some biomass in the recycle stream of fraction x naught, so of concentration x naught, has been sent back, and the outlet is x.